Hello everyone, welcome to my talk. I'm Jie Zhang from UCL. It's my great honor to have this opportunity to introduce our ICSE work, Ignorance and Prejudice in Software Fairness. It's a work that I collaborated with Professor Mark Harmon. Fairness is an important topic in machine learning software. In the machine learning community, we see this abrupt increase in the number of published papers about fairness. In the software engineering community, it is also widely acknowledged that lots of efforts are required from software engineering researchers, for example, in the requirements, specification, design, testing, and verification to guarantee the fairness in the machine learning. And fairness is also one important non-functional testing property that deserves a lot of efforts from software engineering researchers. Let's look at some background on fairness in machine learning software. There is this concept called protected attributes, which means the features of the people that we may have prejudice towards, such as people with different races, genders, ages, and so on. Based on this, the data could be classified into privileged and unprivileged group, where the unprivileged group members they are often at disadvantage. For example, when we try to predict the income, male group is often the privileged group, but female group is often the unprivileged group. So what exactly is fairness in machine learning? Well, there are lots of fairness definitions in the literature, but they could be summarized as the following. So fairness means when privileged groups and unprivileged groups, they are treated equally. For example, they have an equal probability of discern outcomes or predictive performances. Speaking of the bias and fairness in machine learning software, it often makes us think of the bias in people. And the Turing Award winner Yann LeCun once said, "Data is biased, in part because people are biased. Algorithms trained on biased data are biased." And then he said, "Bias in data can be fixed. Bias in people is harder to fix." Its words indicate where the bias in machine learning may come from, but they also inspired me to think about what have we done to reduce the bias and improve the fairness in humans, and whether there is this connection between fairness improvement in human learning and fairness improvement in machine learning. Let's think about how to reduce human bias or human prejudice. Some people may say, "I only know pride and prejudice." Well, that's actually a good start. If you know that pride leads to prejudice, think about what pride indicates. Pride and ignorance, they are closely connected and they mutually beget each other. It's long been recognized that prejudice is the consequence of ignorance. And Kofi Annan once also said, "When we confront ignorance with knowledge, racism can, will, and must be defeated." There is also scientific evidence in the psychology domain that knowledge enhancement leads to less bias, but experience enhancement leads to more bias. So this is in human learning. So in machine learning, there is this interesting connection between feature set enhancement and knowledge enhancement. For example, when we collect more features, it's very much like we collect more information to get more knowledge, to learn more about an object. And similarly, there is this interesting connection between training data size enhancement and experience enhancement. We will get more data, so it's very much like humans get more experiences. So realizing this interesting connection between machine learning and human learning, the focus of this paper is to understand the role of feature set and training data set enhancement in machine learning fairness improvement through an empirical study. So we designed 3 research questions. The first question is about how does enriching feature set affect machine learning fairness? The second research question is to study the influence of enriching training data set on machine learning fairness. And for the last research question, we explore the coupling effect between feature set and training data set enrichment. And we also design a series of sub-questions to dig deep into the results for each question and to get more insights and implications for researchers and developers. We choose 5 widely used datasets in the fairness literature. We also use different machine learning algorithms, and we use 4 fairness metrics to measure the fairness changes. There are two bias mitigation methods that are adopted to check whether they would affect our observations. And we use three analysis approaches to analyze our results. The first is to visualize the results to get a qualitative analysis. And next one is statistical analysis with one-way analysis of variance. For those changes that are statistically significant, we will show their absolute changes and relative changes to give an idea of how big and significant these changes are. These figures visualize the impact of feature set enrichment on fairness. Different lines represent different fairness metrics, and the smaller the values of these metrics are, the better the fairness is. It's easily observed that when the feature set is enriched with more features, almost all the lines drop, indicating that the fairness gets improved. And what's more, almost all the changes are statistically significant, and the average fairness change rate is as high as 38%. Based on this, we get the answer to the first research question. That is, richer feature sets have a notable positive influence on the fairness of machine learning models. And this actually highlights how important feature enrichment is when we try to build fair machine learning software. Second research question, that is the impact of training data set enrichment. Here are the results where the horizontal line shows different sizes of training sets. Interestingly, we didn't observe any unified patterns as we observed for the first research question, which means we can't see that, well, if we use more training data, we could improve the fairness. What's more interesting is that for two cases, when the fairness is measured by disparate impact, the fairness even gets worse when there are more training data, because you can see that the lines go up. Check the statistical analysis results with ANOVA, we found that most changes are not statistically significant. And overall, the change rate is actually below zero. This means that when we enrich the training data set, the overall fairness actually gets decreased. We next dig deep into the two cases where the fairness decreases and try to understand why this happens. So we get the answer by checking the original bias in the training data before applying the machine learning model. It turns out that for these two cases, the bias in the original training data is pretty high. For example, for the adult sex dataset, the disparate impact fairness is as high as 0.637. When the training set size increases, the line actually slowly approaches the original bias in the training data. So this means that when there are more training data, if the training data is very biased, then more data just gives the learning model a better opportunity to learn the bias in the data. Based on these observations, our answer to the second research question is that a larger training data does not mean more fairness. The overall fairness change rate is even below zero. Our third research question is about the coupling effect of feature set enrichment and training data set enrichment. And we visualize the results with 3D surface plots. So we can see that from these plot examples, when there are fewer features, the surface rises more steeply. This observation indicates that when there are fewer features, the negative impact of larger training data on fairness is even more significant. Based on this, our answer to the third research question is that when there are fewer features, the unfairness increases faster with a larger training set. The empirical study has a series of implications for developers and researchers. For example, there is usually this belief that there is a trade-off between fairness and accuracy in machine learning, and if you want fairness, you can't have very high accuracy and your accuracy has to be sacrificed. But our results indicate that there is indeed this sweet point that with more features, it is totally doable to improve both fairness and accuracy. Our results also have some interesting inspirations on previous findings in the psychology domain. For example, scientists found that older adults have a tendency to be more prejudiced than their younger counterparts. This is an observation without enough explanation, so scientists don't quite understand why this happens. Experiments indicate that it might be interesting to further explore whether for those people with less knowledge, they might have more bias when they get older. So to conclude, our work explores the ignorance and prejudice in software fairness. Our work is inspired by human fairness, but in the end, we found this interesting similarity between the solutions to improve human fairness and the solutions to improve software fairness. Our results also suggest more promises in this interesting loop between human learning and machine learning. So we know that machine learning is inspired from human learning, but perhaps human learning could also get lots of insights from machine learning. So in this scenario, the machine learning can be regarded as a simulation of human learning so that we could fasten the human learning experiments with machine learning. At the end of this talk, I'd like to call out that since knowledge is so important in both human learning and machine learning, let's just collect more information and get more knowledge. Let's learn more about each other and better understand each other to fight against bias, prejudice, and racism. Thank you very much for your time, and any questions are welcome.